Okay, so today is this seventh lecture of rings. I guess in the last lecture I have written the seventh lecture, but it was not of second lecture. It was sixth lecture. So today I am going to start seventh lecture of rings, and many things I have covered in the earlier lecture. So let me start with some questions. So because in the last lecture, in the last my board was not properly working, so that's why I'm writing a question here. Okay, first solve this question. I will give you 4 to 5 minutes and you just solve it, and then we'll proceed for the concept, right? So let me start. Okay, so should I write the question? Yeah. So okay, this is the question. Question is, suppose so you know a ring is of C01, right? You should write it by here. C01, what is that? You know, this is actually nothing but set of all continuous functions from 01 to R, which are continuous, right? C01, which is called. So I'm giving you a set. This is I'm defining as set of all functions of C01 such that f of 1 by 4 this is equals to f of 3 by 4 this is equals to 0. So is it so options? Okay, what are the options? A is the ideal of C01. Option B, A is prime ideal. Prime ideal of this. Okay, I'm not writing properly. Prime ideal of C01. Option C, A is maximal ideal. And the D option is none of the above. Which of the following is or are true? Either this one, or this one, or this one, or this one, right? So set of all continuous functions, and I'm defining a set whether you have to verify whether this is the ideal or is a prime ideal or the maximal ideal or none of the above. You have to just verify. Okay, I think the white color is reflecting. No, it's okay, I guess. Yeah, so what will be the option? Still it is giving me, so you just try this one. I'll have to, okay, nothing is here, right? So what is the best thing I can do is pen setting. No, still it is in the same condition. Just a second, sorry for that. I don't know why this is still it is not. So how do I scroll that? Still it is in the same condition. I don't know what should I do. It is not scrolling at all. Yeah, it's okay. Yeah, I think it is fine. So what will be the answer? What will be the answer here? Which one will be the answer? So start. Okay, so I think we should start. So what you have to check for the ideal? I've given you the definition of the ideal, right? So what you have to check? Suppose you have two element inside the member. So solution. Suppose you have two function f and g inside A. Okay. So what does it mean? This essentially implies that f of 1 by 4 is equals to f of 3 by 4 equals to 0, and g of 1 by 4 equals to g of 3 by 4, this is equals to 0, right? These two conditions you have initially. So you have to check whether f minus g and f minus g at 1 by 4 is 0, or f minus g at 3 by 4 is 0 or not. Initially you have to check na for the ideal. What you do to check for whether a set is going to be an ideal or not? First you have to check that a dot a minus b should be in I, right? Okay, and ar and ra inside I for every r inside ring R and a inside the ideal I, right? So this you have to check na. Okay, so this you have to check. So I have to check. This is very easy to check. F minus g at 1 by 4. What is that? F of 1 by 4 minus g of 1 by 4. What is that? This is 0, of course, because this is 0, this is 0. Similarly, f minus g at 3 by 4. This is f of 3 by 4 minus g of 3 by 4. Okay, this is 0. So these two condition, first condition is satisfied. What about the second one? Whether Ra means AR or so whatever. Okay, so suppose let Rx be a member of C01. Rx is a function 001 actually. Okay, and F is a ideal. No, not ideal actually. Yes, F is a member of A, whatever the set is defined as A. Okay, so you have to check Rf at 1 by 4 and Rf at 3 by 4. Rf, that means R at 1 by 4, F at 1 by 4. Because F at 1 by 4 is 0, this implies that this is entirely 0. And similarly, this will similarly work for F of 1 by R, 1 by 4, R of 1 by 4. This is actually FR of 1 by 4. This is actually 0. So first condition is satisfied. Similarly, you can show the second condition is for, second condition is also satisfied, right? The first 1 by 4 is also for 3 RF at 3 by 4. 3 by 4 is equals to FR at 3 by 4. Okay, this is also same. So clearly, so A is an ideal of C01, right? Now the main thing is to verify whether this is a prime ideal or the maximal ideal, right? You have to check for the primality or the maximality, right? Okay, this is ideal. So first option is anyways true. Okay, now we have to check for this and this, whether this is prime or maximal. Okay, so okay, what is the definition of a prime ideal? First tell me, what is the definition of the prime ideal? Prime ideal. Prime ideal means if you have AB inside the ideal I, this should imply that either A is inside I or B is inside I. For every A comma B inside the ring R. If you have the ring R as a ring, right? This is the definition of prime ideal. Or maximal ideal means you cannot squeeze them. If you have an ideal, what is the definition? Okay, let's check for the prime first, whether this is going to be prime. Okay, so define fx is equals to x minus 1 by 4, which is clearly not in A, and gx x minus 3 by 4, which is clearly not in A, because what you have, what is your A? First of all, what is your A? See, A is, if should vanish at 1 by 4, also it should vanish at 3 by 4, but here, see here, it is vanishing at 1 by 4 but not in 3 by 4, and also this is vanishing at 3 by 4. Okay, F is not in A, G is not in A. Okay, because it is vanishing at 1 by 4 but it is not vanishing at 3 by 4. Similarly, G is vanishing at 3 by 4. Vanishing means at 3 by 4 this is 0. Okay, and also if G is not vanishing at 1 by 4, right? So this is not in A, this is not in A. Okay, so what is fx gx? X minus 1 by 4, x minus 3 by 4, which is clearly in A. Is not it? Because this is vanishing at 1 by 4 as well as at 3 by 4. Am I clear with you? Are you getting my point? So fx gx, actually f dot g, it's called f dot g at x. This is actually fx gx, this is inside A. So what is the meaning of that? So we have this. So what is the contrapositive of this statement? Contrapositive of this statement. So if A is not in I and B is not in I, it does not, it implies that AB should not be in I. Okay, so here F is not in A, G is not in A, but it does not imply that f dot g is not in A. I am just taking the contrapositive statement. Okay, so this is the equivalent definition of primality, prime ideal. Prime, if f is not in A and B is not in A is not in I and B is not in I, it implies that AB is not in I. If this implies, then we say that I is a prime ideal. This definition and this definition are equivalent. Okay, are you getting my point? This is equivalent. This is just a contrapositive statement. This if you say this is statement 1 and this is, if you say this is statement 2, this 1 and 2 are equivalent. 1 and 2 are equivalent. 1 and 2 are equivalent. This is the contrapositive of the statement. So f is not in A, G is not in A, but it is does not implying that f is not in A. Okay, if this implies that AB is not in A, then this is it. So this is not a prime ideal. So A is not prime. Are you getting my point? So let now check for the maximality. So this option is false. Now check for the maximality, whether this is going to be maximal ideal or not. Maximal ideal. What is the definition of maximal ideal? If you have an ideal I and this is contained in any ideal J, this is contained in the ring R, then I either I equals J or J equals R. Okay, are you getting my point? You cannot, then we say I is maximal. Then I is maximal if this happens, right? So you cannot squeeze between, you cannot allow any ideal in between them. So if there is any J is another ideal which is squeezed between I and R, then I cannot be a maximal ideal, right? So maximal ideal, are you getting my point? The definition of the maximal ideal. So okay, so what do you think about the option C, that whether this is maximal or not? For maximal ideal, so let's define. So define a set M which is actually all those functions inside C01 such that f of 1 by 4 this is equals to 0. Okay, so this is easy to check. This is easy to check. M is maximal in C01. Why this is easy to check? Because you cannot, if f is f1 by, so this ideal is a maximal ideal. Okay, you verify it. So this ideal is a maximal ideal, right? If this is a maximal ideal, also you can verify that this A is properly contained in M and M is contained in C01. So if this happens, so this cannot be a maximal ideal. M is a maximal ideal. Also M is an ideal. First of all, M is an ideal, or A is contained in M, because see here, what is my point? My point is, you see here, try to understand what is my M. See here, A, what is my A? A is all those functions inside C01 such that f of 1 by 4 this is equals to f of 3 by 4 actually 0. It vanishing at exactly 2 point. And what you have defined as M is all those function f inside C01 such that f of 1 by 4 is 0. Can't you? So you can verify A is an ideal. At least you can show that this is an ideal. Verify. This is very easy to show. This is an ideal. Also, can't you see that A is properly contained in M? Because M is exactly 1 point, it is vanishing, but A is vanishing exactly at 2 point. Can you see? A is properly contained in M because A is vanishing exactly at 2 point. There is two restriction, and there is only one restriction. So this is already contained in here, and this is also properly contained in here. You can verify, right? So A is an ideal. Our ideal is A. We have, there is a proper ideal M. This is properly contained in M, and M is an ideal of our ring. What was our ring? C01. So this cannot be maximal, right? A cannot be maximal. Cannot be maximal, right? Are you getting my point? It cannot be maximal because there is one more ideal which is properly contained in here, and also M is not equals to this C01. Okay, so this finishes the proof that A cannot be the maximal ideal, right? What was our question? So this is also false. So the correct option is only A. A is only an ideal. Okay, so now I think we're done with the question. Now let me introduce something, and I will prove something here. So I am writing some statements. Try to see and try to prove. I will prove it. Do not worry. So should I? So let this F plus dot be a field. So now I am going to prove the statements here. So my question is, can F plus be isomorphic with F star dot? That means this is the set of all units. So are these statements are valid or not? Any finite subgroup of F star dot is cyclic, and the third one, F star p की power n dot is cyclic. What do you think about these statements? Are they are the statements actually make sense? Make sense or not? If they make sense, then can you prove or disprove them? So I'm going to prove the first one, second one, and third one, right? So proof. How do we prove? So whether first statement is true or false, I don't know. So I will prove that first statement F plus and F star dot are never isomorphic. The first proof I am going to that F plus and they cannot be isomorphic. How do you show? See, if F is a finite field, okay, F is a field. Have I mentioned? Yeah. So F is a finite field. F is a finite field. If so, case 1. If F is a finite field, if F is finite, this implies we are done, because it will contain exactly, suppose if contains n elements, so it will contain n elements, and F star means set of all units. Unit will F star dot means you are eliminating 0, so there is one element which is not inside F star. Okay, so we are done. Okay, why we are done? Because if f has n element and f star has n minus 1 element, so if two they are different, cardinality is different, so they cannot be equal, they cannot be isomorphic. So case 2, how do we proceed for the what is the case 2? If f is infinite field and characteristic of field is not 2, f is infinite field and characteristic of f is not 2, that means f is not actually Z2. Okay, because Z2 is a Z2, that means the field with characteristic 2 are very special field, so we cannot consider here. So we are assuming that this is infinite and the characteristic is not 2, right? The field of characteristic, that is f is not Z2, that's it. Okay, so how can we proceed for that? If f is not f is infinite field and characteristic f is not 2, so how do we show that this is not, they are not isomorphic? So let me define, let phi is a map from this f star or f, that we set of all units to f. How do we define the map? Be as a group I be any group isomorphism, suppose they are isomorphic, be any isomorphism, suppose there exist. Okay, they are isomorphic as a group. Okay, so there is one operation. Okay, so anyways, so if this is to identity here, identity 1, it should go to identity here, identity 0, additive identity 0, here multiplication, this is under multiplication, this is under addition. Okay, so the identity goes to identity, right? So how can you write for the identity? You can't you write it as the phi of -1 into -1? What is that? What is phi of -1 plus phi of -1? Because this operation is under plus and this operation is okay. So what is that? This implies that phi of 1, what is that? 2 phi of -1, right? So this implies that. So what is phi of 1 is 0. See here, this is 0. So 2 of phi of -1, this is 0, right? Since the characteristic is not 2, so you can write is phi of -1 is 0, which is the contradiction, which is a contradiction to the fact that see 1 is also going to 0 and -1 is also going to 0. So this is highlighting the fact that if is, so isomorphism means it is 1 1 on 2 and homomorphism, right? So it is violating the 1 1ness. This is 1 is going to 0 and -1 is also going to 0. It is violating to the fact that f is, this is a contradiction to the fact that f is 1 1, because I have assumed that this is an isomorphism. This is an isomorphism, so it is violating to the fact that isomorphism, right? So I think you are clear. So this cannot happen if the f is infinite and the characteristic of field is not 2, they cannot be isomorphic. So f cannot be isomorphic to f star. Okay, so this has been over. So now you have one case left. What is the case? Case 3. F is infinite and characteristic of f is 2. How will you proceed for that? Suppose you have similarly, suppose define an isomorphism. Suppose you have an isomorphism. Let this phi is from f to f star. F to f star is an isomorphism as a group. Okay, isomorphism. So if it is isomorphism, so here identity goes to phi of 0 is the identity, and this is goes to 1, it definitely should go to 1, right? And suppose, so yeah, suppose phi of 1, this is alpha, say, okay, suppose I've assumed alpha is a member of f star, alpha is a member of f star. Okay, so what are the choices? Suppose you can write it phi of, see, you can write it -1 plus -1. So what will that be? Phi of -1 into psi of -1. Are you, let me write clearly. See, this is, here is operation, here is operation plus, and here is operation dot, here is plus. So what is that? Psi of -1 into psi of -1. What is that? This is actually psi of -1 that square. Are you getting my point? That means, okay, the psi of -1, okay, what is 1 and what is -1 here? Can you predict? So here, see here, so in the correct, in yeah, so what we have is psi of -2, this is actually psi of -1 that square, but you are in Z2, that means the characteristic of field is 2. So can't 1 is not, 1 is equals to -1, 1 and -1 are same na, in characteristic in Z2 1 and -1 are same. 1 is congruent to 1 mod 2 and -1 is also congruent to -1, sorry, 1 mod 2, right? In the characteristic 2, 1 and -1 are same. So, and -2 is means 0 in characteristic 2, -2 means 0, and here -1 mean -1 as 1, I have 1 third square. What is that? So psi of 0, what is your, sorry, what is your phi of 1 is alpha square, because this is alpha and this is alpha square, right? So what you have is this, you have psi of 0 is equals to alpha square. Okay, so alpha square, and we have psi of 0 is 1. What you have? Also you have psi of 0 is 1. Okay, so in equality, so since they are equals, since they are isomorphism, so they must be 1 1 or 2. So psi of 0, so alpha square should be equals to 1, this and this should have to be same. So alpha square should be equals to 1. Okay, alpha square should be equals to 1, right? So now alpha minus 1 third square, what is that? Actually this is alpha square plus 1 minus 2 alpha, it's not it, just. So what is plus 1? Plus 1 is basically nothing but -1, because 2 is equivalent to 0, 1 plus 1 is equivalent to 0, that means 1 is equivalent to -1. Are you getting my point? In Z2, in characteristic 2 field, characteristic field 2, this, they are all equal. So what you can do is, see here, this is alpha square -1 and is 2 alpha, this is going to be 0, -0 in Z, since our characteristic of the field is 2. Okay, so this is alpha square -1. What is alpha square? Alpha square equals to 1, this implies 1 minus 1, this is equals to 0. So alpha minus 1 third square, this is equals to 0. This implies that alpha equals to 1. Am I clear? Okay, so alpha minus 1, see, alpha is, See here, alpha square is 1. I've just written here alpha. So alpha minus 1 plus square is 0. That means the alpha has to be equals to 1. From here you can see here, right? So this has to be equal. There is no other choice. So what we have is, see here, psi of what is minus 1? Minus 1 is 1, right? Alpha na. Yes, 1 is alpha, right? Okay, 0 is 1. Why psi of minus 1 is? Because 1 and minus 1 are same. 1 is alpha. See here, 1 is equals to alpha, and what is the value of alpha is 1. So what does it mean? Psi of minus 1, because 1 and minus 1 are same in the field Z2. This is 1, and this is also psi of 0. See here, psi of 0 is alpha square, and alpha is 1. 0 is 1. In fact, this from here psi of 0 is 1. So this is contradicting to the fact that f is 1 1. Sorry, psi is 1 1. So it cannot happen. So this f plus cannot be isomorphic with f star dot. They cannot be isomorphic. Here also I have written f, not f. This is actually phi. That is bad habit from all the functions are from f. So that's why I have taken that f is 1 1. So anyways, so this is clear, right? So this I have proved. Now what about this? 3 statements I have written, right? What about this statement? Okay, I think this will not work here. Anyways, there is no problem. No, I think there is, yeah. So what is that? Thinking option. So I am writing again, okay? No problem. This is not working, na? Okay. So what the second, any subgroup of, what was the statement here? Let me just see. Any finite subgroup of f star is cyclic. As a group, okay. That I will prove. What will be the proof? How do we prove? This proof is little bit lengthy, little bit abstract, okay. So this proof may not, there is, I have one field, okay, and I have the collection of all units of the field, okay. So I will have to prove that any finite subgroup of this is cyclic. So see, this proof may not be a little easier for everyone. So I will prove this one, and this proof might seem that it might not be in front of anywhere. So anyways, I will prove it, no problem. You do not have any problem. So just a second, I am doing something here. Okay. Okay, so how do you prove it? So there is two cases I will assume here. Okay, how do you prove? So suppose that so if you have f is a field and f that is the collection of all units of f. Okay, so suppose that HB any finite subgroup of any finite subgroup of f star or f, okay, units. So suppose an order of h is n, which is finite. Okay, my claim is h is cyclic. How do you show h is cyclic? So you have, let d divides n. So if d divides n, so what do you think about x to the power d minus 1? This equation, this equals to 0 has at most d root or d zeros. It's not it. This equation has at most d zeros. Okay, because some of them may repeat, right? So this equation has at most d zeros. Okay, so this equation has at most d zeros. So how do you prove that this h will be is of cyclic? Suppose that case 1, you assume that this case 1, h has an element of order d, and suppose this element is r. H has an element of order d and say it is r. H has an element of order d, suppose, and r is an, that means r is an element of h and order of r is d, that means r to the power d is identity. Okay, are you getting my point? Okay, so r is an element of h and order of r is d. Okay, so what will be the order of the generated by r? See here one thing, this is a subgroup, right? This is a subgroup of h. In fact, this is a cyclic subgroup of h, and order of this generated by r subgroup is d, because this r is of order d. Okay, so order of generated by r is d. So now can you feel that this generated by r is totally contained in all those elements such that x to the power d is 1. Can you feel that? See here, this has exactly d elements. This set has exactly d elements. D elements. And what can you think about the d elements? Can be this r is totally contained in x to the power d is equals to 1. Can you think? Why this is? Show how. So let me just giving let me suppose I'm taking that, let x be any element of this generated by r. So what does it mean? If generated by r is a subgroup, okay, this is a subgroup, this is a subgroup of h, right? So suppose x is an element which is inside this subgroup. So and this subgroup has order d, so d will divide the order of x. This implies that, or sorry, order of x will divide d. Till now it is clear. Suppose that order of x is k, so k will divide d, that means this from here. So what does it mean? This implies that d equals to some kl for some l inside integer. Okay, Okay, right? So what is x to the power d? X to the power d. So x to the power d. What is x to the power d? X to the power kl. What is that? X की power k to the power l. This is equals to 1 because x की power k is order of x is k. What does it mean? This implies that x की power k is 1 na, identity na. So this implies that this x to the power x is, this implies that this x is inside this set, x is inside all those x inside f star such that x की power d is 1 because x की power d is 1 na. Okay, so this implies that this set is contained in x inside f star such that x की power d is 1. And can't you see they are equal because this has exactly d elements and this has at most d elements. So d has exactly d element, it has at most d element, but this is contained in here. See a set here, two set here, one is contained in another, but it has less element, it has bigger. So can't you see? So here you cannot see, so you cannot. So see here, this has exactly d elements and this set is inside at most d elements. So can't you see they are equal? This and this has to be equal, right? There is no other choice in your hand because this has exactly d element, this has at most d elements, and this is contained in here. This set is contained in here. So from here, so it is easy to verify or easy to check. There is no other because these are exactly d element, it has at most d element. Okay, and d element is already here. Okay, it has exact at most d elements and it has minimum d element here, it is contained in here. So this is very easy. So basic things, or what is it, this is trivial. So this kind of things are trivial. So what you can say is this is actually equals to right. Am I clear? This is x to the power d is 1, right? X to the power d is 1. So can you see the proof now? So for every divisor d of n, you have a set. So n is divides also n. So if n is divided, so for n you will get a set like that. For every divisor d you are getting a set like that. So for every n, so you will get a such that x to the power n is 1, and this set and this set are equal. You will get an element, right? So can you see the proof now? So why h is cyclic? Why h is cyclic? So we will get this, right? For every divisor, for d we are getting this. For every n is also divisor, so for that we will get that. So this proves the theorem. This proves that h is cyclic for case 1. Now what are the case 1 here? The case 1, h has an element of order d and say it is r. Suppose there is no element of order d, order such d. Suppose case 2, there is no element of order d, okay, and order of h is n. So you have to show that h is cyclic. So we know a theorem here. What is that? Summation d divides n, phi of d, this is n. Okay, so here, so if there is no element of order d, so it will not be satisfied, it will violate. You know that, I guess everybody should know that this well-known theorem, that summation d divides n, phi of d is equals to n. There is a group theoretic proof, there is a number theoretic proof here for that. So you know that if d there is no such element of order D. So this will not be satisfied, right? This equality will not be satisfied, because we have to satisfy the summation D divides N, phi of D, this is N, but D, all the divisors, D divides, but there is no element, no such element. There is no such element of order D here. D divides N, but there is no such element of order D. So this will not be satisfied. This will violate. This will violate the fact, right? So it cannot happen. So H has to be cyclic. H has to be cyclic. So for every divisor there is a, for every divisor, that means there is an element of order, that element or order of that. Okay, so every divisor should divide, right? Otherwise this will not satisfy. So H is cyclic. Okay, that's proof. That's proved the theorem. And what was the third proof? The third one is just nothing but, if you prove the second one, if you understood the second one, then third one is nothing. There is nothing new in the third one. Third one is says that this is cyclic. So see here, every any finite subgroup finite subgroup of dot is cyclic. So this is cyclic. How do we show this is any finite subgroup of F star? So F star is, this is itself a finite subgroup of, I mean finite subgroup of F star dot. So this is the application of this from here, from 2. This is easy to verify, right? When easy to verify means this is obvious, trivial. Okay, so that's finishes the theorem. I am giving you one question, not question. I'll have to prove. I'll have to do some more concepts here. I'll define quotient ring here, right? So I will define quotient ring. QUOTIENT, quotient ring. I will define. So before that, I am giving you a break of 2 minutes. Just a second. Sorry. Yeah. Just a second. 2 minutes. I am just coming. Quotient ring. Okay, so I think I should start. It's night, 1:40 am, 1:49, 1:50. Anyways, let me set up the situation. Okay, what is quotient group? First of all, you should know about the quotient groups, right? So you should know what is a quotient group. So similar thing, and what is quotient space, and similar thing is here, right? What is a quotient ring? So for quotient ring, so you need, so for quotient group you need a normal subgroup, right? So what do you expect here? So what do you need here to define a quotient ring? You need an ideal, right? You know, at least you should definitely, it should comes in your mind that you need an ideal here, because in group you need a normal subgroup, right? That then only you can define the quotient. So here you need an ideal. So what you need is, so let me define, let R be a ring. Whenever I am writing R be a ring, you should definitely understood, it should be understood that R means there is two operation, plus and dot, right? And plus operation is first and second operation is dot. That means not as usual plus dot, but just a just for the formality, there is two operation, plus and dot, right? So and I be an ideal of R. What is R by R mod I? This is called R mod I, right? This is defined at R plus I, such that R is inside R. What is the operation? Plus operation you can define as R1 plus I plus R2 plus I. This is actually R1 plus R2 plus I, and R1 plus I dot R2 plus I. This is actually R1 dot R2 plus I. Okay, this should satisfy for every R1 comma R2 inside the I, sorry, inside R. So this forms a ring with respect to plus and dot. This is called a quotient ring. Quotient ring, and quotiented by I. Okay, are you getting my point? Now this is just the definition of quotient ring. Okay, now let A be an element of the ring. So what is generated by A? This is actually defined as intersection of all ideals containing A. This is intersection of all ideal containing A. You can also write it, this is the smallest ideal containing A. Containing A. Similarly, you can define if S is a subset of R. This is not necessarily subring, and you can also define this S generating set. This is called the smallest ideal containing S. Containing S. For example, I am giving you a question here. Example. Suppose, what is R? Your R is, suppose, ZX. Polynomial rings in one variable, and your ideal is generated by X. Ideal generated by X. Check R by I. What is R by I? And I is prime, maximal. You have to check. So your ring is the polynomial rings over Z over integer, and your I is ideal generated by X. What can you expect from R mod X, R mod I? That means ZX by ideal generated by X. And what do you think about whether I is a prime ideal or the maximal ideal, or prime and maximal both? What can you say about that? So think about it 1 minute, then I will definitely solve this question also, no problem. Okay, so you have to check for armoured eye, right? Okay, so I should start. You can pause and solve it in yourself. Anyways, so can't you see that you should have to verify that this ideal generated by x, ideal generated by x is actually nothing but this x px. Px means the polynomial whether px is inside zx. Mosquitoes are here. That's too much. Okay, so px inside zx. Can you see that this ideal generated by is this? Just give me 1 minute, right? Because I have to. So can you see that this px or x, this ideal generated by x is nothing but x px, such that px inside zx. Can you see? I will show that this x, I will show that these two are equal. Why these two are equal? See, can you see that this ideal, this I is contained in this set? Suppose call this set as A suppose. Can you see that this is contained in A? Because this I, the ideal generated by x, is the smallest ideal containing x. Okay, so you will have to verify that this A is an ideal of R, that means zx. Okay, so if this is an ideal, and this will imply that I will, because I is the smallest ideal containing in A, containing, so this must happen, right? So because I ideal generated by x is the smallest ideal containing x, and this ideal is contains x, and this is also an ideal, so this implies that I is contained in A. Okay, so I is contained in A. Now we have to prove the reverse part. How do you prove the for the reverse? How do you proceed for the reverse? So you have to prove that A is contained in I, okay, or I contains A. Okay, so this is clearly because I is an ideal. What is A? A is actually, you have written x px, such that px inside zx, right? So this, why? Because I is an ideal. I is an ideal. So r dot I and I dot r is contained in I for every r inside R, and Yeah, for every r inside r, because I is an ideal, so this will contain in here because I is the ideal generated by only x. So x dot px is contained in I, right? What is your ideal? So this is an ideal, right? So this is also clear. So now you can verify, you can show that I is ideal generated by x, and the ideal this x px are equal. Px inside zx, this is, they are equal. Am I clear with you? So this ideal is nothing but this ideal. Okay, so now in fact for NEA, this is for the particular example, right? So for NEA, in fact for NEA inside the ring R, this ideal generated by A is actually A dot R. A dot R such that R is inside the ring R. R should be CRU, right? Commutative ring with unity. So what? So now you can define this quotient ZX mod ideal generated by X, which is actually nothing but ZX inside PX. That means ZX means PX plus what is ideal generated by X. That means, okay, this is actually px dot this and px inside zx. Okay, this is our quotient ring. Also you can verify, this is your homework. This ideal generated by X is also all those polynomial Px inside Zx such that P0 is 0. Okay, verify this is an homework. So you have to check this X is prime or maximal. Prime or maximal. Okay, what is the definition of prime and what is the definition of maximal? I have just few minutes earlier I have recalled the definition of prime and maximal, right? Now you have to check whether this ideal generated by X is going to be a prime ideal or the maximal ideal, or prime maximal both. What do you expect? Let check for prime. Let me change the color. Yeah, so suppose that px qx should be inside the ideal generated by X, and you have to show, if it is prime, then you have to show that px inside, either px inside X or qx inside X, right? This should imply that px, either px inside X, qx inside X, right? So my claim, my question is, so suppose you have two polynomial, right? So this is inside the inside the ideal generated by X. Suppose px is, suppose that a0 plus a1x plus dot 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 plus an x to the power n, right? And b0 plus b1x dot 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 plus bn x to the power n, right? So this is inside ideal generated by X. So what do you expect if it is ideal generated by X? So if this is ideal generated by X, so you have to P0 Q0 should be in 0, because all those functions, all those polynomials here such that P0 is 0. If it is an ideal generated by X, then P0 Q0. What is this? Is my P, this is my Q. So P0 0 Q0 is 0, right? So P0 is a member in Z and Q0 is a member in Z. So two integers are going to be 0 if and only if this implies that if and only condition P is inside is ideal generated by X or Q is inside ideal generated by X, because there is no other choice, because P0 this is in P0 is a P0 this is inside Z, because P0 means the constant term, P0 means the constant term, Q0 means the constant term. Two integers, the multiplication of two integers is 0, then one of them must have to be 0, there is no other option, right? So this implies that this ideal generated by X is prime. So what can we expect for the maximality? Okay, so we'll go check for the maximal. So now what do we think about this ZX quotiented by ideal generated by X? You know, this is actually Px, this is definition, right? Px inside ZX, right? See here, A plus I equals to B plus I. For quotient, what you have said, AH equals to BH if and only AB inside A. So similar argument is work here, A minus B inside I, right? And also this is an important notion. Yeah, suppose you have an element 2 plus this ideal generated by X. So what do we think about see here, this is an element in ZX mod ideal generated by X. It is clear because 2 is an element of ZX. So what can we think about it? Is it a zero divisor? Zero divisor. Is it a unit? Is it a okay, zero divisor and unit and zero element. What do you think about that? What do you think? Is it a zero divisor, is it a unit, or is it a zero element? So check for them. See, one element is 0 when this element is, suppose you are checking for the 0 element, right? This suppose, so 2 plus X, what is the 0 element? Is ZX mod X is X, right? If it is 0 element, if 0, then if it is 0 element, then 2 plus ideal generated by X is this, right? So this happens if and only if 2 inside ideal generated by X, but 2 is not inside the ideal generated by X. This is a contradiction, so it cannot happen. So this is not, so 2 plus this is not a zero element. I am not talk about the zero divisor yet, right? So mind it, I have not talked about zero divisor. I am just talking about whether this element is a zero element or not. So this is not zero element. So how zero element will look like here? So zero element is of the form this. So if this is zero element, so it will of the form, because I am using this here, two quotients A plus I equals to B plus I if and only B minus B inside it. So that's it, right? So is it a unit? So if I can show unit, so I will automatically get zero divisor whether it is zero divisor or not, because if it is unit, it cannot be a zero divisor. We have proved. Okay, I think you can recall. Okay, is it a unit? So for unit, this 2 plus this or you need another polynomial, another element, this it should give you this unity, right? It's not it. If A is unit, if there exists a B such that A dot B is equals to 1. This is the definition of unit now. So I have exactly this definition I am using here, right? So what does it mean? This means that, so what is the quotient operation here? 2px plus this is equals to 1 plus this, right? So two quotients are same if and only if 2px minus 1, this is inside ideal generated by x. If and only if, see here, this is 2px minus 1. So see here, what is ideal generated by x? What is the definition of ideal generated by x? Ideal generated by x means p0 should be 0. So if it is inside the ideal generated by x, and ideal generated by x is nothing but p0 is 0, so this if and only condition 2p0 minus 1, this is equals to 0, right? So this will imply that p of 0, what will be 1/2, right? So can there be a polynomial that takes half value? That means this is a fraction, this is not inside the integer. So no polynomial in zx. See here, p0 means p0 means the constant term, okay? Every terms involving x will be 0, and you will only left out with the constant term, right? So constant term cannot be half because you are in zx, because you are in zx. So how the constant term can be half, because half is not a member of the z. So no polynomial zx that takes half value. So that takes half value. So this 2 plus this is not a unit. So if it is not a unit, it must be a zero divisor. So it has a zero divisor. This implies that this is, so if it is not a unit, so can you say this is a zero divisor? So it is not, so this is going to be, this is not a unit, right? So let's for the zero divisor. Okay, yeah. So if it is not a unit, so it does not guarantee that it is a zero divisor, right? So there may be some element left out that is not a unit, also not a zero divisor. So anyways, so let's check for the zero divisor. Zero divisor, right? So for zero divisor, you have two non-zero element, but still it should give you 0. So let's 2 plus this, and there is, you have, I'm writing at p, only p plus this, you have this, and it is giving you the 0 element. So what does it mean? This is 2p plus ideal generated by x is this. Two ideals are same if and only if 2p is inside x. What does it mean? Similar argument, similar 2p0, this is 0. If and only if p0 is 0. This implies that p0 is 0. What does it mean? That means that this implies p inside or px inside ideal generated by x. If px inside ideal generated by x, if P is in ideal generated by X, then P plus ideal generated by X is ideal generated by X. This is already here, this is already contained in here, this is already a member of that. So P plus ideal generated by X is nothing but ideal generated by X. Are you getting my point? P plus ideal generated by X is P plus ideal, because P is already an element of the ideal generated by X. So this implies that this P and this is a zero element. Are you getting my point? P plus, why P plus X is, why P plus X is this P, see here, this is a non-zero element and this is a zero element. If you are trying to get to non-zero element and you are still giving it, you are expecting that it should still give us zero element, that is the ideal generated by X. So you are getting what you are getting, that this is a, so this is a zero element, so this is not a zero divisor. So 2 plus ideal generated by X is not a zero divisor. If you are getting, if you want to get some P plus X, you are getting that P plus X is nothing but zero element. So you are getting a zero element, right? So there is no purpose, so it cannot be a zero divisor. Okay. Anyways, so what are the zero divisors then in PX, in ZX? So what are the zero divisors? Let's try to find the zero divisors. What are the zero divisors? What are the zero divisors? Suppose that you have PX ideal generated by X, QX ideal generated by X is 0. That means ideal generated by, in the quotient ZX by RX, ZX by ideal generated by X. So it can happen only if PX QX plus ideal generated by X right? So this is, it can only happen that PX QX should be a member of ideal generated by X, and this is only can happen that what is ideal generated by X, it should satisfy P0 is 0. I am repeating this again and again, right? See here, this is, see here, this I am repeatedly I am using this. This Px is nothing but all those polynomial in Zx of the P0 is 0. So what does it mean? If it is inside the ideal generated by X, what do we expect? That P0 Q0, it should be equals to 0, right? So this, if and only if P0 is a polynomial, P0 inside Z and this is inside Z, this is a polynomial in Z, and P0 is a constant time, this is inside Z. So this implies that P0 is 0 or Q0 is 0. If P0 is 0, so P0 is 0, Q0 is 0. If and only if P0 is 0 means if and only Px plus X plus ideal generated by X is this X, and Qx plus ideal generated by X is X, ideal generated by X. Are you getting my point? See here, P0 is 0, Q0 being 0, that means Px, see Px inside the ideal generated by X, right? Px inside ideal generated by X, Qx inside ideal generated by X. So if this happens, so Px and this they are automatically they are either or, or either this 0 or this 0 there is. So it has no zero divisor. You cannot, I am not able to find any zero divisor, so it does not have any zero divisor. So either this has 0 or this has 0, so it has no zero divisor. So this zx quotiented by ideal generated by x has no zero divisor, hence it is an ideal integral domain, hence it is an integral domain. But why can you is it a field? So answer is no. Why? Because in field every non-zero element should be an unit, but is 2 plus whatever the element we have, this is not a unit. It's not it. You see here initially what we did here. So okay, for a unit we have checked here, right? Check for zero divisor, what no, check for unit. Yeah, this is not a unit, right? We have proved. So every non-zero element should be an unit, but there is an element which is not an unit, so it cannot be a field. So it is means the zx by ideal generated by x, that means is not a field because of this. Okay, this will imply here, from here to here, this statement will imply that this is not a field. This statement will imply that this is not a field. Okay, we have left out with the maximality. Okay, so we have not checked yet the maximal, whether this ideal generated by x is maximal or not. What do you think about the whether this is going to be maximal ideal or not? What do you think? Is it a maximal ideal? So if it is not maximal, so you just have to check whether this if you can find any j which is in between x and zx, and which is also an ideal, and which properly contains the ideal generated by x. So what do you think? Suppose you have this j 2 comma x, ideal generated by 2 element, that is 2 comma x. What is that? This is actually defined as px into 2 plus qx into x, such that p comma q inside z. Are you getting? That means z means zx. So what do you think about whether 2 is inside? What do you think what 2 can be? See, 2 is inside j. what is this? Is actually ideal generated by 2 comma x. But 2 can 2 in be in ideal generated by x? 2 is not in ideal generated by x. So this is an ideal. You verify that this is an ideal. And this ideal is contains an ideal generated by x. Properly contains, is not in fact contains, it properly contains an ideal generated by x. So this x is properly contained in J, because this 2 inside J, but this 2 is not is inside the ideal generated by x. Okay, are you getting my point? So this, but my point is, and this is inside not R, actually the ring Z. But what do you think about them? Are they equal or not? But how do you know this is they are not equal? This J and ZX is not equal. Why? Can there also be something? There also these possibilities also occur that J and ZX are nothing but they are equal. But how do you know why they two are not same? Then only you can say that this is maximal, right? Otherwise you cannot say that this is not maximal. Not maximal unless you verify that J is not ZX. You cannot say that this is not maximal. This ideal generated by x is not maximal. See here. See, ZX contains 1. This is a ring with unity, commutative ring with unity, right? But what do you think about whether 1 is inside? Think. 1 is not inside here. How do we generate 1 from here? Px into 2 and qx into x. How do we generate 1 here? Can you tell me? You cannot generate 1. You cannot generate 1 here. Okay. So what is unable to sync charges? Please check your connection. No. Yeah, I think. Okay. I think I should have to stop. Just a second, please. I don't know. My board stops working after 2 hours. I guess 2 hours also has not been covered yet. That's not a problem. That's not a problem. No. Yeah. So how can you generate 1 from 2 comma x, ideal generated by 2 comma, it cannot, 1 is not inside, so this J cannot be equal to ZX. So what you have is, you have an ideal, this ideal generated by x is totally contained in J, but this J is not equal. J is actually this ideal 2 comma x, 2 comma x, ideal generated by 2 comma x, and this is totally contained in our ZX. Are you getting my point? So this x is not maximal, but it was prime. We have proved, right? It was prime. So should I move further? I have to cover many things. I don't know. Okay, let's analyze one thing here. That this, what do you think about the ideal generated by 2 elements? That means 2 comma x. What is that actually? So let's come to that. So what is the ideal generated by 2 comma x? What is that? You have pretend that this is actually px dot 2 plus qx dot x such that this p comma q polynomial are from zx. Ideal generated by 2 comma x, and this is an ideal of this ring, right? Whatever the ring is, this ideal generated by this ring, right? So what you can expect here, you can write as a polynomial, you can write as a summation ai x to the power I is from 0 to n into 2, right? This into 2, right? And this q is, you can write it as j from 0 to n bj x to the power j, right, into x. Can't you write whatever it is? Sorry, ai bj, sorry, such that ai comma bj are inside from z. Okay, can't you write? Okay, if you can write that into 2, so this into x, so you can merge them, right? Of course you can merge them. So 2a0 there will be x. So what will be the first? The constant term will be 2a0 plus what will be the second term? 2a1 x, and here will be x square term, and you will only left out with one b0 term here, right? So b0 term will be there. So what you can expect, that 2a1 plus b0 plus what is the next term you will have? You will add 2a2 here, a2x square, and you will get the x square term in before that. So 2a2 plus b1 plus dot 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 such that ai comma bj inside from z, right? What is that? Can't you see all this polynomial px inside zx, such that all those polynomial px inside zx such that p0 is even, constant term is even. Okay, are you getting my point? P0 is even, p0 is the constant term, all those polynomial, this is an even number. Are you getting my point? Px means all the constant term is this, right? So this p0 should be even. This 2 comma x, that means ideal generated by 2 comma x is nothing but all the polynomials in zx, so that p0 is the even number. p0 is the even number, right? Because a0 can be anything here, whatever the a0, this 2 will multiply by this a0 and this will still be the same. Okay, that's it. So I think that's for, I guess, if I define the matrix ring now, so this will definitely take some time. So let me define just matrix ring. After that we will do the ring homomorphism in the next lecture. Ring homomorphisms, yeah, after that I will define. So let me define matrix ring. I already know, just I will define in what is a matrix ring. So matrix ring, because my board is matrix ring. What is matrix ring? You know the matrix group, So let R plus, so R be a ring. If R be a ring, R be a ring. So if you have R be a ring, so Mn, you can define Mn R. Let me just a second. Yeah, I think this color I should choose. So what is the best? So you can define Mn R. What is Mn R? Set of all n cross n matrices which entries are from the ring. So A equals to Aij n cross n, such that Aij inside the ring R. Okay, this is actually the matrix ring. So this is the definition of matrix ring. Okay, so that I will not define more here. Okay, yeah. So okay, now one more question I will ask here from here. So is this max ideal? Whatever the ideal I have written in the first, this is the ideal generated by 2 comma x is maximal. This question I have left. Is this maximal? So what do you think about whether this is maximal or not? Let me think a little bit whether this is going to be a maximal or not. So you just think whether this is going to be maximal or not. Suppose just go with the definition. So if it is maximal, so we can define this J. So okay, I will define some. Okay, so yeah, so I think I should start. What we will do here, so you know the definition of the maximal ideal, right? So you need to find this 2 comma x. This is if it is maximal, if it is not maximal, right? So suppose that if J is a maximal, no sorry, J is a ideal. Suppose if that what this 2 comma x ideal generated by 2 comma x is properly contained in the ideal J. Okay, so what is ideal J? Suppose this 2 comma x, what is 2 comma x? This all those polynomials as the p0 is even. So if it is properly contains in J, this means that what is this implies that there exist px inside J, there inside J, such that this p0 is odd. P0 is odd, right? Since this is properly contained in J, that means there exists a polynomial P inside the ideal J such that P0 is odd, right? So let P0, which is actually odd, suppose this is n is odd number. Okay, so 2 is a member in J, right? And n is odd. This implies that GCD of 2 comma n is 1, GCD of 2 comma n is 1, right? So this, since whatever the odd number is and 2 is the even number, so it cannot divide, the GCD should be equals to 1, right? If the GCB should be equals to 1, so this implies that 2L plus NK this is equals to 1, right? This is the property of GCD. You can write as the linear combination of this two L and K integer for some integer. Okay, you have to understood. So this is inside J and this is inside J. Can you see here, 2 is an element in J and n is odd number. So and GCD of 2, and you have GCD of 2 comma oh my god, there is no charge in my laptop. Okay, so GCD of 2 comma n is 1, so you can write as a linear combination So what does it mean? This is an inside J and this is inside J. So this implies that 1 is a member of this J. This implies that this J 1 is this is inside the ZX, because 1 is a unit, because this is a unit. Okay, because this is a unit, so this J contains a unit, so J has to be equals to the entire ring. Okay, so we have proved that if J contains if ideal contains, or any ideal contains an unit, so it will be equals to the entire ring. Okay, you might ask one question here, why NK is inside J? So why I have told that why inside this is inside J. You should definitely ask this question, because 2L is inside J. This is clear. This is generated, the ideal was generated by 2nx. So why this NK inside J? Why NK is inside J? You definitely have to this question, but think about it first. Now I am telling why NK is inside J. What is my J? J is an ideal, right? Which does not contain this ideal generated by 2 comma x, right? 2 inside J, so 2L inside will definitely be inside J, right? And this 2 comma x is already contained here. So why NK inside J? My question is why NK inside J? So define Hx is equals to n minus px. What is h of 0? N minus p0. What is my p0? What is my p0? P0 is n. This implies that n minus n, which is actually 0. Am I clear? Does this imply that h is inside J? H of 0 is 0, right? So h is inside J. Since p inside J and also h is inside J, so h plus p will be inside J, right? Are you getting my point or not? If you are not getting my point, then please. So Hx is equals to, I have defined this in such a way such that at 0 this is 0, so it will definitely imply that this ideal will be inside J, right? What is my J? So this implies that H is inside J. If H is inside J and we already have P is inside J, so this will definitely imply that H plus P will be inside J. This implies that see P is inside J, so it will definitely imply that H will be inside J, because P will be definitely dominated. Okay, so H inside J. So what is my H? See here, P inside J and H inside J. So how? P inside J and H inside J. How do you think? What is P? H plus P. What is the value of H? H is n minus px. N minus p plus p. That means n minus p plus p is inside J. This implies that n is inside J. If n is inside J, this implies nk is inside J. Are you getting my point? So that this is why this nk is inside J. There is no. Okay, so that's all. So this is equals to J. So that's why. So this this ideal 2 comma x is maximal. In Zx. Are you getting my point? This ideal is a maximal ideal. See, I am repeating the proof why this is maximal. 2 comma x inside J, so J is an ideal. So this 2 comma x, so here 2 comma x is inside J, right? So ideal generated by 2 and x, suppose this is completely contained in J and this is not equals to J, so it means that there is an element P, there is a polynomial P inside J such that Px is odd, P0 is odd, because we have defined this ideal as P0 is even. So there is at least one ideal, one element, there is at least one polynomial P such that P of 0 is odd number. Okay, so P0, suppose P0 equals to n, which is odd number. So 2 is inside J, because 2 comma x is inside already, this is already contained in here. So 2 inside, of course, inside J. So n is odd number. So GCD of 2 comma n is 1. So this implies that 2l comma nk, 2l plus nk will be 1 for some l, for some m l comma k inside Z. So this implies since 2l inside J and nk is inside J, 2l is inside J, this is clear. But why nk is inside J, I have given you the explanation why, right? So 2l inside n, 2l plus nk will go to 1. So this is inside J, this is inside J, so 1 must be inside J, because this plus this equals to 1 and 2 addition will be there. So 1 inside J. If 1, so 1 is unit. So 1 contains, if J contains unit, so J will be entire Zx. Prove the theorem. Okay, so if you are regular following the classes, then you don't need to worry. I guess you are not stucking, and only stucking were jump to the lecture number 7 directly. So that's my point. So 1 is inside J. So this is, since this is a unit, if it is unit, so it is entire. So J equals to Zx. So there is no such ideal between generated by 2 comma x and Zx. You cannot dominate so you cannot dominate, right? So in between them there is no such j. J is equals to this. J is nothing but this. Okay, so why this nk is inside j? I have proved it. I have defined this. H0 is 0 is 0. This implies that h is inside j. Whatever h is, why see here 0. What is h0 is 0. H of 0 is 0. 0 is even or odd? It's even number as well as odd number. So this is inside j, right? Are you getting my point? This is inside j. If it is inside j, so and p is already inside j. P is already inside j. P is a polynomial. We have already, there is this p is already inside j. This h plus p will be inside j. So h, what is h? N minus p plus p inside j. That is n inside j. If n inside j, nk inside j. So this is a maximal ideal, right? So that's all for today. Next in the lecture 7, lecture 8, we will define ring homomorphism. This is an important, and we will do the isomorphism theorems, first isomorphism theorem, second isomorphism theorem, and third isomorphism theorems. So that's all for today. So good night to everyone. We'll meet in the next lecture. Thanks.